So let's look at this proof of the Cauchy-Schwartz inequality, which is done a little differently without using the angle between two vectors. So let's write down a hypothesis. So V and W are vectors in Rn. Then you get the Cauchy-Schwartz inequality, right? So that's magnitude or absolute value of V dot W is less than or equal to magnitude V magnitude W. So let's assume the vectors are in Rn. We'll break this up in two cases. So if either are 0, that's it. We're done. Nothing else to do. So I'll write that out. So if either V is equal to 0 or W is equal to the 0 vector, that is, then the inequality holds, right? You just get 0 is less than whatever. 0 is less than 0. So less than or equal to, that is. So then the inequality is true. So then 2, we will assume they're not. So assume V and W are not equal to the 0 vector. All right, so this is one way to do it. So we're going to let A be a real number. And we're going to look at magnitude of AV plus W quantity squared. That must then be greater than or equal to 0. All right, so I'm asserting something that must be true, which is this. So now we're going to look at that. We're going to expand that out. So we have magnitude AV plus W squared is equal to AV plus W dot AV plus W. Same as we did above, really. Now let's multiply that out. So it's equal to AV dot AV plus 2A V dot W plus W dot W. That's using the distributive properties of dot product. And let's simplify that a bit. That's equal to A squared magnitude V squared plus 2A, and just rewriting that as V dot W plus magnitude W squared. Oops, I should have just started over. Little notation stuff. Okay, so magnitude W squared. All right, so we're going to call that f of A. So that is a function of A. So we want to look at this basically as a function of just A, and we're going to fix V and W. So here's A squared and then 2A, and it ends up being a quadratic. So what you do, we hold V and W fixed. So fix V and W. Then F is a quadratic polynomial. Then F is a quadratic polynomial and must be non-negative. Okay, so why, you may ask, why must it be non-negative? Because it is being expanded, where to go? Here. Right, so I expanded that out and got this. So this must be non-negative due to that. Okay, so I sometimes I like to just put a little star next to that to refer back to why, because of that. So the minimum, so now we basically take derivatives. So the minimum value of f occurs when f prime of a is equal to 0. Right, for some a, right? I mean, there exists a value a when it's minimum, so it must basically open up. So that is, that is, i.e. Did it again. That is f prime of a equals, and now I'm just taking the derivative with respect to a, right? So it's just 2a magnitude v squared plus 2 v dot w, and then that other was a constant, so it's gone, equals 0. If and only if a is equal to, so now I'm just solving, so I have this equal to 0, and now I'm just solving for a. So subtract and then divide. So you get a is equal to negative v dot w over magnitude v squared. And remember, our v's and w's are non-zero. Okay, so then, so quadratic polynomial, basically what I'm implying here is that it has one minimum. So it must occur when it's 0. So that is its minimum value. So the minimum value of f is at a. So this a. And we have f of that value, which is negative v dot w over magnitude v squared. So I'm evaluating to get the minimum value of f. And it must be positive, which is what we're going to use. So we substitute in this whole thing for a, which is here. Where's my function again? I'm putting it here and evaluating. So I get v dot w over, squared, over magnitude v squared minus 2 v dot w squared over magnitude v squared plus, and then this doesn't change, magnitude w squared. So just take a look at what I'm substituting. So this here is being substituted here and here. Okay, so you see how that worked, basically? And then let's see. Making sure it's right there. Squared, yeah. So when you squared this, you ended up with another one of these down here, and then it reduced with that one. So that's why it stays on the bottom there. Just double check that. Okay, so then we can factor out the v, so a little messing around, and check this out. You get magnitude v to the negative 2 times magnitude v squared magnitude w squared minus v dot w squared okay, so basically rearranging this, so factoring this out, and then simplifying and factoring, and you get this. Okay, so that's I maybe did too many steps at once there, but check that out. See how you could get that. That must be, because of our assumption above, or our assertion above, greater than or equal to 0, even though it's minimum. That's greater than or equal to 0 because of this same, where'd it go? Same hypothesis here, that these are both positive, magnitude squared has to be positive. And so that has to be a minimum value, and it's still positive. What that gives us then is this right here must be positive. So this, as we know, is positive. That means this must be positive as well. So in that case, what you get then is almost the inequality we want. So you get v dot w squared is less than or equal to magnitude v squared magnitude w squared. And now just square root both sides and you're done. So square root both sides and you have it. So if you do the square root of a square, you get absolute value anyway. So you get v dot w in absolute values is less than or equal to magnitude v magnitude w. And that proves Cauchy's Schwartz inequality without using an angle between them. So go through it again. It's a little different. It took me a while to find this proof because it doesn't sit with me very well to talk about angles between two vectors in 5 dimensions. So this is essentially saying this has to be positive. It's a polynomial. What's the minimum value can be for any a? Well, it's this value, and it has to be positive because it's what you started with. And then if this is positive, then this has to be positive, which gives you this, which gives you the inequality, right? This difference has to be positive. You can't do a product and get a negative, and therefore you have the inequality. Okay, that's it for chapter 1.2. Going on to 1.3, talking about matrices next.